So good morning, everyone. I'm Zhe Bai from Dev Group in CRD, and today I'm going to talk about the computed tomography image segmentation and registration for traumatic brain injury analysis. So understanding traumatic brain injury study is a huge and valuable challenge to social goods. It usually occurs in transportation accidents, falls, and sports. So people suffer from this physical injury, and then they begin to have physical, psychological, social, and spiritual influence in their life. So just to give you a sense like how complex the data we handle. It's a very big multimodal data set we collected from radiologists, and each individual patient scan contains tens of millions of voxels, and you could imagine by combining a cohort, large populations data, this needs significant computational efforts. And the social impact applies to every aspect of our life. So for example, we like to watch football games, and this weekend will be the Super Bowl, right? And we love the football player, and we don't want them to suffer from physical injuries in their later life. So the goal of this project is to leverage computer vision and data science to further study the spatial structures of traumatic brain injuries, brain tissues, and localize their deformation, as well as developing machine learning techniques to detect and predict outcomes for them. So let's start by looking at some data we have. On the left side, you see a MRI template, which is a typical MRI template in biomedical domain that people use it a lot because you see very good resolution, very good contrast to start from. But in reality, what we really get is something on the bottom right. So you see that's the CT scan from a traumatic brain injury patient, and basically you don't really see a lot of contrast in it, and that's where we started from. At the end, what we want to build is a reasonably good CT template that we could take as a reference to compare and contrast the large population CT scans. And how we are gonna get in there is this. Is what I'm going to talk about in this project. And one thing I want to introduce you first is image registration. And this technique basically started from early this century and began to mature recently. It has tremendous use in real experiments or measurements because usually we don't collect data from the same coordinate. They're all less in different space or coordinate. We have to put them together, align them in the common coordinate so that we could analyze the data in scientific way, right? And if you look at this figure I'm showing on the bottom, it's saying we could deform a half C to a full C by really distorting and tilting the grids, right? So you see the mesh changes over the couple of snapshots, and eventually we could warp this half C to C. And how we realize this is a technique called image registration. And you could similarly imagine how we could warp a single patient's CT scan to a template by doing the same procedure. And let's talk about the registration framework. It usually contains three main parts. Deformation model, which basically assuming you have a good model to start from. It could be linear, nonlinear, it could be local or global. And you want to find a good matching criteria. It could be intensity-based or feature-based. And you also want to find a good way to optimize this problem. So I will walk you through some of them in this last slide. When we talk about deformation models, usually we want to start from linear in rigid and affine space. And then we assume there's a vector field in diffeomorphism that could register the source image to the target along a geodesic path. And how we find this geodesic path is by minimizing the energy along an arc. So on the bottom right, I'm showing the velocity field or vector field. You could imagine in this registration process from a fixed image and the moving image. And by basically integrating this vector field throughout time, you eventually find this geodesic path. So just give you a big idea about what I'm doing in this project, and the pipeline is shown on the left. So we start from pre-processing data, and we do image registration and segmentation. We collect measurements from this visual imaging, and then by extracting features, we eventually build this statistical modeling to find the patterns in the data. And this final goal is to help radiologists with their analysis in precision diagnostics and prognostics. So let's look at some detailed procedure what I'm doing in this project. So first, on the top left, that's the original CT scan. You could see in the original data, and you see, like first, we want to find a good processing methodology. Basically, you want to redo the image orientation. You want to resampling it so that every CT scan could be in the same resolution in voxel size. And we correct the bias, and we also pre-align it to MRI, which is the typical MRI template I introduced the slides ago. And then we do a skull stripping so that we could literally look at the detailed information about the tissues itself. Okay, now we collect a large amount of CT scans with skull stripping. And we want to do is a good CT template, and how we approach that. So CT template is basically, we say it's a reference that we want to register all of the patient's CT scans to it, because it's a common coordinate in an optical sense. So we want to do this study by subgroup. So what I mean by that is, people's brain are different, and especially a differentiate from age and gender. So particularly, we subgrade to divided it to 6 groups based on age and gender, and then in each subgroup we collect multiple data, and on the average sense we generate this template. And in the algorithm sense, it relies on linearly rigid and affine transformation, and also in the nonlinear transformation, as I said, we basically leverage diffeomorphic mapping among a group of diffeomorphism because it could guarantee a smooth mapping function and the inverse. And from the performance side, we want to have an efficient algorithm. So this image, in this preset, the image similarities are parallelized through multiple cores on our working machine. So eventually, this is the template we generated from a large amount of CT scans. And you might think, this is kind of magic, how you could just average all of the original low contrast CT scans to this template. And let's see how it got involved over the increasing number of CT scans we used. Okay, so in this animation on the left side, it shows how the image quality could improve over the number of subjects we use, from 4.8 until 128, 158. And if you see the quality plot on the right, we could see basically around 128, we basically obtain a pretty good resolution and the contrast in terms of the imaging quality index. So that's a number we will keep using for all of the cohorts. And then what we are going to do after we receive this good template, we are going to register every individual scan to this template by doing the same optimization process as I mentioned in the image registration. And by finding this geometric transformation, good geometric transformation, we could do this iterative algorithm over step by step, and eventually, when it converged to a certain tolerance, you are good to start from. Then we say like this subject is aligned or registered to the template we want. Okay, and then after we register all the subjects, what we are going to do with the segmentation. And this is an interesting part because if you think about the template and the brain atlas, and when I say brain atlas, it means a map basically labeling all the important tissues of a brain. It's just think about a map. For example, we say California is in the map of United States in West Coast, right? South of Oregon and Washington. And that's the same thing if you look at the brain atlas. And if we register all the image from the physical space to this MRI space through the affine transformation and the diffeomorphic mapping, eventually we could map all the brain atlas back to their physical space by doing the inverse mapping we obtained from the registration process. So let's look at some results. This slide is showing the cohort group study of template we obtained from the registration. And you see the variations among those subgroups in terms of the age and gender. One thing we observe first maybe the ventricle part, which is localized. Let me see whether I could point it out here. Which is localized as a interconnected part in the middle of the brain, as you see in the dark part. So if I extract this ventricle, you really measure the volume of this ventricle differently in subgroups, right? So, and the interesting thing is when we compare our segmented ventricle volume to the recent study characterizing how the ventricle volume differentiated from age and gender, it really matched a deep learning result published last year using tens of thousands of people's data. And that's quite interesting because we use much less data and obtained a similar trend here. Okay, so and that also explains why we want to do this subgroup study, because this significant feature will differ from people population in terms of their age and gender again. Okay, and now let's look at some case study. So this one is showing a severe patient's CT scan. And first, again, we do the skull strip, and you see the brain tissue. And we register it to the CT template we just created, as you see on the upper left. And on the lower right, I'm showing the deformation map, which is what we obtained through this registration process. And the brightest part basically highlights this individual's injury. Like we localize where of this CT scan has the most deformation among all of the voxels. Okay, and then in the segmentation result, you see based on the atlas used, you could map it back to the physical space or the template space, and you could segment each individual scan based on the registration. And if you look at the cortical layer segmentation, this is an atlas we used basically from Harvard Oxford result about a decade ago. And the thing we observe is it's sort of symmetric in terms of the labeling because there's no difference between differentiating left to right plane of the brain. So that's where we want to improve. And we also want to combine the cortical and the subcortical layer together. So we have a detailed characterization about the details about the brain itself. So in this slide, I'm showing 115 labels, basically combining all the cortical and subcortical postulations together. And what we are going to do with this atlas. Okay. So now what you see is the segmentation result across a range of severity or TBI conditions. On the first row, what you see is the typical atlas we obtained by combining the cortical and subcortical of cells. And then on the second row, you see a mild patient's segmented brain, and on the bottom, you see a severe patient. And what we've shown in this slide are all in the physical space. So that's why you see the different shape of the brain, which is the real case. And then, okay, we segment the tissues, and now what? We want to characterize the measurements. We want to see how we want to take advantage of the deformation information to fit into the machine learning model, right? And this is showing the same patient segmentation result in the physical space, as well as in the template space, which is the MRI. Okay, if you look at the detailed information about the deformation, if I just look, subtract the mean and the sigma, you see the data is pretty different in terms of how they vary in this local region. And so by subtracting, by extracting those information, including mean, sigma, and the higher order terms, as well as entropy, we also include the geometric measurements, for example, volume, surface area, and the elongation thing. We build a good feature matrix, basically includes 10 features in each subregion, and we combine all of them into our data matrix for feeding into the machine learning model. And on this slide, I'm showing the statistical result about our template creation. So, you know, we divided the people into 6 groups and build the templates. We don't want to introduce any bias in this lab, right? And this is showing through PCA and UMAP, we really see a similar trend about similar distribution about all the first and second component of all the template we obtained. And that's basically mean we don't introduce any significant bias among this study. Okay, and the further correlation analysis result indicates us how this outcome component is correlated with the CT measurement we obtained. And along this linear fitting, you could basically see the severe patients sort of outliers in this plot. And also the darker dots here are showing patients that eventually will get a severe condition over hospitalization. So we think this is pretty promising because if we could predict the outcome throughout the visual CT imaging, that will be significant to the field to both surgeon and radiologist work. Okay, so just to summarize really quickly, in this study, we generate a new CT template that doesn't exist before in good resolution and contrast, and we contrast the good amount of population in their 3D CT scans. And the measurements we got from the neuroimaging itself really correlate with the outcomes. And we want to do further about the biomarker study. And we also think, you know, this methodology is very general. It could apply to different types of imaging and other types of sensing data. And in terms of future work, we want to further improve the algorithm side in terms of improving the registration process by feature matching and build a automatic brain morphology pipeline and to further, you know, facilitating the clinical case. And we also, as I said, we also want to include the clinical data for this outcome prediction. And we also want to work on the algorithm side to further realizing the parallelization such as GPU use. And in terms of the extensions, we want to see whether this methodology could apply to time sequence data, for example, the macroscopy or material science data set, and as well as beamline data. So that's that's it. And with this, I want to thank my mentor, Talita, my collaborator, Andrew, and Chris in this project, and all the insightful discussions and evaluations from UCSF. And I'd like to take your questions. Thank you for your attention. Yes.
I have a question about, so you said that when the hotspots show the injuries, right? So if I understand it right, you take the average of these images in a way and you create a template, see for that class. And then you basically register the image to that template. And in the places where there's higher changes to the template, like where, so right, if you're taking the image and you're registering it to the template, when the places in the original image that show the hotspots are the parts that deform a lot to basically to get to match the template takes a lot of energy.
Yes.
So that means that's where you find the brain.
Oh yes. So in terms of the energy part, so you want to find a geodesic path along this registration process, and that's how you want to leverage optimization to minimize the energy, right? So that's the part when I mentioned the energy. And in terms of the deformation itself, eventually you could think about it as a deformation matrix, right? And this is basically showing how this matrix looks like visually, right? And basically the largest voxel value will indicate the part that's deformed the most, and that's also the injury information. Thank you. Yes.
Is there could you go to the slide where you discuss your objective function in machine learning?
Sure.
It's one of the initial slides where you were trying to minimize the. So yeah, what is the physical justification of using this kind of energy function that involves? Can you talk more about why we use this specific objective function? I think there's one more previous to this slide where you talk about the objective function.
And can you repeat the question? Oh, the velocity field.
Yeah.
Okay.
Can you talk about what is this function?
So the question is about the optimization formula, why I formulated it, and what it means. Okay, I could certainly elaborate it. So if you look at this optimization function, the M indicates the mutual information, and we want to maximize the mutual information among this mapping. And the I and J are the fixed and moving image, and the phi is the transformation or mapping function, you could think. It's basically a time-varying function. And that on the right side, the vector field indicates this vector, right? Like this vector, how it could get integrated through time. And also, this function need to be constrained in a certain space. And that's the T. It's a group of space. You have to guarantee that this transformation wouldn't go beyond your imagination.
And in your study, you used 153 samples for training your the template, right? For creating those templates, you said you used 153 samples.
Sorry, could you repeat your question?
In your figure where you showed you used 153 images or 153 subjects, is 153 enough? 158, sorry. Is 158 enough for creating this, or have you seen what happens if you actually increase it further?
Yes, that's a good question. So I repeat the question is about how I could guarantee 158 is good enough for the image quality, right? And this is what I'm showing on in the animation on the left. Basically, there's no there's no limit. Like you could always go better and better. I mean, you want to stop at some criterion you're happy with. And the real thing is, this is real data. This is a real study. We don't really have huge amounts of data, right? Like CT, if you think about CT scans, the first thing that doctors would ask TBI patients to do is to take their CT scans in emergency. But usually, people who take the CT scans would suffer from X-ray radiation, right? So we generate a template actually not based on the TBI patients, but on clinical data close to normal people's brain. And then we register TBI patient data to this template. And if you look at this animation again, increasing the number of subjects, you see a pretty good characterizing about the contrast and tissues in the brain, and we are happy with it. Again, like I think you could go further and further in better sense, but first we are constrained by the limit of data, and second. Actually, that's a good question. Maybe eventually, if you overuse too large number of data, you may saturate the template, and eventually it's not a good representation about the whole group. Did I answer your question?
Yeah. Again, this is further. Thank you.
Any more questions?
Okay, thank you for the attention.